Greetings of the day. My name is Amit Juyal. Today I am here to present my paper ID 37474, Modified Vehicle Detection and Localization Model for Autonomous Vehicle Traffic System. So these points we will discuss today: introduction, problem definition, YOLO V5 architecture, methodology, improved model, pose intention of a cyclist and a pedestrian, customized data set, result, and then conclusion. So, a self-driving is an intelligent autonomous driving feature that improves the safety and the convenience beside the control. Some international automakers have already launched and are operating self-driving automobiles, like Tesla, Waymo, Zoox, Cruise are a few examples. The overall intelligent driving system includes camera, radar, lidar as the primary sensors that are used to collect the data about the nearby traffic, as shown in this figure. The visual information is provided by the camera. The distance and the velocity of the object are determined by the radar, and the 3D point clouds are nearby traffic are produced by the lidar system. Software based on the deep learning, machine learning, and pose estimation model process these data which are collected from the hardware like camera, lidar, radar, and etc. And further processes this information to estimate the object and intention of the observed object, and based on these outputs autonomous vehicle system control itself. So all the car manufacturers in India have already deployed advanced driver assistance system, but a fully autonomous vehicle still requires significant improvement in the complicated system of autonomous vehicle. On Indian roads, a wide variety of vehicles are in use. People modify their vehicles to meet their specific requirements. An illustration of one such vehicles is seen in this figure, in the figure 2A and 2B. Therefore, an intelligent vehicle system that can recognize and detect all category of vehicles is necessary for the safe driving in autonomous vehicle. So figure 2 illustrating the image of modified vehicles. By attaching the carrier to the motorcycle, it is transformed into a cargo or transit vehicle. So our deep learning model should be capable to detect these type of vehicles also, so that autonomous vehicle can take the decision and can make a decision uh, according to the type of the vehicles. The operation of an autonomous vehicle depends on the accurate detection of a fixed and moving objects. As shown in this figure, figure 3, the illustration shows that this figure shows that the autonomous vehicle is following uh, its predetermined path. The autonomous vehicle planned route may include crossroads. Fixed objects like barricades and traffic cones may be used to restrict one or both sides of the intersections. Barricades and traffic cones can restrict the flow of cars, trucks, buses, and other vehicles, but cyclists and pedestrians can bypass these obstacles. Cyclists and pedestrians can cross in front of an automated vehicle by going over permanent barriers like barricades and traffic cones. Accident may occur due to these circumstances. Consequently, an autonomous vehicle fixed for an autonomous vehicle, fixed and moving object is essential to detect for a safe driving. The object detection challenges involve identifying, locating many objects in the digital image. To resolve the issue of object detection, till now various machine learning and deep learning techniques have been applied. An important computer vision issue is real-time object detection, especially when it comes to autonomous vehicle or autonomous driving. Compared to conventional techniques such as CNN-based techniques with good mean average precision are being focused for a real-time traffic detection in autonomous driving. Basically, object detection method is of two types: two-stage object detection and one-stage object detection. The method like RCNN uh, based on the conventional neural network perform detection in two steps. With the first, region proposals are generated using the segmentation and selective search, and second, it tries to find the object in each region. The YOLO V5 architecture is a the YOLO family is a one-stage object detection. Okay. So YOLO V5 network is comprised of three critical components: convolutional neural network and optimized spatial pyramid pooling, generate visual features at the uh, various levels in the backbone, neck, and several layers that integrate and mix visual features before passing them for a prediction. The head part of the network processes the feature from the neck to perform bounding box prediction with class labels. However, in real-time detection system like autonomous vehicle, more accurate and agile detection is required for safe driving. The present study focuses on developing a deep learning model that can detect both stationary and moving objects for a safe driving. Secondly, the study aims to detect the intention of the pedestrian to cross the road. So this is the methodology. Real-time object detection of a fixed object as well as moving object is an important task for a safe driving. The primary risk concern for self-driving is a real-time scenario is the detection of multi-class object like dynamic objects, cyclists, pedestrian, various types of vehicles, as well as static or fixed object like barricade, traffic cones. Multi-class object localization is an essential problem in computer vision, containing numerous applications like self-driving cars, security systems, X-ray, and many others. The challenge derived from the above discussion is known as multi-class object localization, and it plays an important role for the autonomous vehicle because due to this technique, various objects present in the surrounding of the vehicle can be detected, classified, and located in the term of their exact positions. So this figure display the entire diagram of the suggested framework for the detection of multi-class dynamic and fixed object in the real-time traffic scenario. In the first step, the moving object and the fixed object are detected using the improved YOLO V5 CBAM model. To enable autonomous vehicle to operate safely, the next stage is to detect the object that have been modified. Additionally, recognizing stationary objects like traffic cones, barricades, and traffic signs is crucial for the self-driving automobiles. Although barricades and traffic cones are used uh, as a fixed items to control traffic, it has been observed that the pedestrian, cyclists, and the two-wheeler riders often disregard these types of barricades and can emerge abruptly in front of any car. As a result, in the Indian traffic scene, pedestrians, cyclists, and two-wheelers are seen as a potential accident cause. Therefore, it is crucial for safe driving to detect pedestrian, cyclists, and the two-wheelers, and the intention of pedestrian, whether they are crossing the road or not. So, in the present study, we have improved the original YOLO V5 model, and the original YOLO V5 object detection network normally comprise the neck, backbone, and the detecting head. The feature retrieved in the middle networks are noticeably low, which causes the detection result of YOLO V5 for the Indian traffic scene to be less than optimal. Even though the original YOLO V5 can detect and identify automobile in vehicle images with good accuracy, it only requires a small number of parameters to suit the information because there are similar vehicle images that can be detected with the fewer parameters. The proposed YOLO V5 CBAM model addresses uh, the limitations of the YOLO V5 model in the vehicle detection job and provide three major contributions. In the first, as shown in the figure, a cross-stage local network called CSP is employed to integrate and generate image features on many lightweight convolutional neural networks for better adjusting the depth of the network. The base layers feature map is split into two partitions using the CSP approach, which then integrate them utilizing a cross-stage hierarchy. Unlike the YOLO V4 network, the YOLO V5 CBAN network structure has two CSP structures, CSP1, CSP2, with the first type of mostly utilized throughout the backbone and other one being primarily used throughout the neck. The YOLO V5 CBAM network produces four output feature maps having various size of comparison to the YOLO V5 network. Secondly, the efficiency with which the intermediary layers extract the crucial data determines the success of object detection. The YOLO V5 backbone model extracts the images features and uses them to detect object in the digital image. From the from the extracted features, some features have a greater influence on the outcomes than other. As a result, we require a model that can solely concentrate on the key features. Therefore, we have added an intention components in YOLO V5 to focus on more important features for the attention module. The convolutional neural network distributes the higher weights to more important features and lower weights to less essential information. The weighted data is then combined and evaluated. Three categories can be used to classify common attention modules: the hybrid attention modules, the spatial attention modules, and the channel attention modules. The hybrid attention module is a lightweight attention modules that generate a channel attention map and uses this information to generate a final fine-tuned feature. In the spatial attention module, in the channel attention module, each of the channel of a feature map is viewed like a feature detector that concentrates on what is important given an input image, and the spatial attention module is responsible for allocating weight for the spatial data. The CBAM, which is made up of the channel and the spatial attention module, CAM and SAM respectively, is the attention module that is added to the YOLO V5 network architecture. In the improved YOLO V5 CBAM, the CBAM layer is added in the backbone after every CSP1 layer, and in the neck part, it is added after every CSP2 layer so that the network can focus on more important features. The primary motivation for utilizing CBAM in the improved YOLO V5 CBAM is that it is an impressive attention module for CNN that can efficiently extract the information about the channel and the spatial attention. And the third improvement which we have done in YOLO V5, in the traditional YOLO V5 there are only three heads, but in the present study we have added an extra head in the improved YOLO V5 CBAM to generate more features. YOLO V5 CBAM with four heads in YOLO V5, which was originally developed, three detection heads make it possible to detect objects of different size. In the improved YOLO V5 CBAM, there are four heads layer regarding the object detection. The number of detection head in the is equal to the number of feature maps scale on which the predictions are made. So the next phase of our study is to estimate the pose of to estimate the pose intention of a cyclist or the pedestrian. So in this section, based on the detection of the both cyclist and the pedestrian, the technique of using the pose estimate as a primary information to ascertain whether the cyclist and the pedestrian will cross the blocked road using fixed object is investigated. In the proposed model, the intention recognition algorithm is integrated with the object detection algorithm to anticipate the intention of the detected cyclist and the pedestrian. The figure shows the flow of object detection along with the pose estimation using the PAF method. To construct a 2D pose for both the pedestrian and the cyclist, the first step is to use YOLO V5 CBAM to detect the pedestrian and then input that location into the path affinity fields method. The orientation and the pose and the position of the pedestrian limbs are represented by the 2D vector fields of PAF. The PAF means a path affinity field. The PAF architecture is used in the pose estimation process to acquire the 2D feature of the individual present. So YOLO V5 first take the input, and in the input it detects the fixed object like barricades and the pedestrian, and then we are applying the PAF model. The PAF model estimating the pose, the skeleton of the pedestrian. So in this way, our model can estimate the pose intention of the cyclist or the pedestrian. So customized dataset for testing and training of improved model. YOLO V5 already have a good performance in vehicle detection. The uncertainty in Indian traffic scenario make it more challenging for YOLO V5 in real-time traffic object. Figure 9 clearly illustrates that the YOLO V5 produce false result due to the lack of Indian vehicle information. For the present study, the custom dataset is required so that our proposed YOLO V5 CBAM based model can detect normal Indian vehicles but also modified automobiles also. To assess the effectiveness of our suggested methodology, we have created an entirely novel set of Indian traffic object dataset. Images of vehicles and stationary objects from Indian traffic situation have been collected in Dehradun, city of India. 2,740 color images have been gathered. The figure showing that yeah, the original Yellow 5 detect an illegally modified vehicle as a motorcycle. It is shown in the figure. So so this is the modified vehicle. Uh, so original Yellow 5 detecting this vehicle as a motorcycle, but it is actually it is actually a illegal modified vehicle, uh, which you can see in normal traffic, in Indian traffic. And the second image, the original Yellow 5 is detecting is like a truck, but it is a public transport Vikram. Uh, and this is again, this is the e-rickshaw, which is showing in the figure C. The original Yellow V5 detect it as a truck. So we require a data set so that we can train our model on these type of images, so that our model can detect these object as a correct object. Okay, so in this way, because of this reason, a customized data set for testing and training is required. Result. This section depicts the result of the real-time testing based on the mean average precision score of the developed model. The experiment finding indicate that the YOLO V5 CBAM network outperformed the YOLO V5 network. The figure 11 illustrates the initial YOLO V5 M model achieving a mean average precision MAP of 41.3% after being trained for 300 epochs. There has been a significant improvement in the average recall rate, average recognition precision, and other performance measures, particularly for a classification task with similar items. As a result, it is appropriate and reasonable to use CSP and CBAM to extract the key feature, which in turn serve to improve network detection layers and increase the identification efficiency of similar Indian traffic objects, modified cars and static objects. With its detection results of 98.2% MAP and 98.4 precision shown uh, in the figure 12, and 94.8% recall rate, which satisfy the requirements of the static and dynamic object detection. It may be said that the suggested YOLO V5 CBAM network perform the best overall in the task of object detection. The table 1 represents the comparative value of MAP precision recall acquired by our model. With original Euro V5 M model, it is clearly shown that our model has achieved the better result in comparison of a YOLO V5 CBAM. So, so our YOLO V5 proposed YOLO V5 uh, is achieving a good precision, good mean average precision 98.2, while YOLO V5 small is have only 37.0 mean average precision. YOLO V5 medium has only acquired only 41.3 mean average precision, and YOLO V5 extra achieving only 50%. And model, our improved model performing very good results. So these are the generated graphs. So the box loss graph represent the model efficiency in predicting the bounding box compared to the ground truth. After training, in the box loss graph, epochs are on the x-axis and the box loss is represented on the y-axis. When the training starts, initially the box graph loss start at a high level and steadily decreasing with the progress of training. The box loss graph validation box loss graph during validation is also decreasing after every epoch. YOLO V5 CBAM is a multi-class object detection method that can localize and predict the class of object in the real time. Class loss graph represent how efficiently YOLO V5 CBAM predicts the class score. Class loss during the training and the validation should be minimal. The class loss graph train class loss and the validation class loss illustrate that the proposed model is doing good in predicting the class score because the class loss is gradually heading towards the minimum. Another loss function known as a distribution focal loss DFL loss capture the object detection aspect of the capability of the model. If the model is extended to perform multi-class object detection, rather than accepting the bounding box coordinator as a scalar value, DFL takes the bounding box coordinator to the distributions. The position of an object in an image can be described more correctly if it is set as a probability density rather than the point. The focal mechanism in DFL gives the higher emphasis on making samples that are challenging for the selection and more difficult to predict during the learning process. During training and validation, the DFL loss is leading towards minimum value, which represents that the proposed model is performing better object detection with the multi-class prediction. Now, the conclusion. In the context of the best result, the mean average precision is the measure of to evaluate the model performance. The proposed YOLO V5 CBAM model achieved the good result in the object detection in comparison with the other YOLO-based model networks. An intelligent transport is a necessity in the modern traffic scenario. Self-driving or autonomous vehicle, which is an integration of an artificial intelligence and advanced hardware, is the key technology in intelligent transport. Real-time decision making is a very important factor for a driving in autonomous vehicle. Computer vision shows excellent possibility in autonomous vehicles. It is an artificial intelligence field that can provide vital visual data from nearby traffic that can be helpful for autonomous vehicle to decide whether to go left or right or to accelerate or apply to brake accordingly. Real-time detection of various static and moving traffic participant is a critical in self-driving cars. Fixed object in traffic scenes includes barricades, barriers, and traffic cones. A real-time detection method for the Indian traffic system is proposed here on a custom dataset containing images of dynamic and fixed traffic objects. Concerning precision recall and mean average precision, the enhanced YOLO V5 CBAM model and the original YOLO V5 network have been trained and evaluated on different scales. The experimental result showed that the proposed YOLO V5 CBAM achieved better MAP than the original YOLO V5 on the multi-class object detection. Pedestrian and the cyclist may came across the autonomous vehicle. The possibility of autonomous vehicle collision with pedestrian or cyclist is handled using the PAF approach, which identify the bikers, pedestrians intend to cross the road. Future studies have to have the potential to extend the current work. Future study can expand the dataset to include more diverse image of different illuminations, blurry images due to the motions, and images with noise from unwanted lights in rain or snow. The proposed model can detect images in real time. Autonomous vehicle can be used it for driving in uncertain traffic, such as in Indian traffic scenario. Apart from this, it is also meant for discovering new ways to enhance detection according accuracy and speed in real time application like autonomous vehicle. Thank you.